There we go. So yeah, final December 9th is a Wednesday at 12:30. So again, this problem we're going to do, you don't have anywhere. If you want to write stuff down, write down this stuff in the box. I'll give you like another 5 seconds to write that down really quick if you're trying to do that. This question is similar to one you'll see on your homework. It's essentially, it's 5-5 material. So remember 5-5 was we were using the fundamental theorem of calculus to essentially solve for antiderivative values at a certain point. So say we have this set of information. So technically the full problem, a lab is performing tests for a new drug. They were testing how long it stays in someone's system. So capital D is the amount in milligrams of a drug left in a person's body after X minutes. And then little d is equal to capital D prime. So essentially that just means that the capital D equation is the antiderivative of the little d equation. And that's the rate at which the drug leaves a person's body. And given the information below, evaluate the expressions. I'm not going to interpret them just for the sake of time, but so say I wanted to find what capital D of 0 was. So essentially the antiderivative evaluated at 0. So if we think about that in terms of kind of 5-5 material, remember that when we calculate an integral, it gives us antiderivative values. So essentially what we'd want here, based off the information that we're given, is we're going to want to use an integral that has a 0 in it, and we have to know the other antiderivative value for the other bound. So we have like these two integrals here that include 0. So to use the first one, we would need to know what the antiderivative at 4 is. But we are given that, where is it? Right here. And then for the second one, we would need the antiderivative at 7, which we also technically know that as well. So technically there's 2 ways we could do this one. So I'm going to do both of them. So say we wanted to use the integral from 0 to 4. Well, if we think about what that means in terms of the fundamental theorem of calculus, this is the capital D of 4 minus D of 0. And so we want D of 0. So if we do a little bit of algebra here, well, let's plug in the values that we know. So we know that the integral value is -3. And D of 4 is given to us to be 5. So if we do some algebra here, say we add D of 0 over to the other side. And then we add 3 over to the other side. We end up with D of 0 is 8. And let me just do the other way as well. So say we had instead used the integral from 0 to 7. Same idea, this would give us D of 7 minus D of 0. We know what the integral value is. We're given that it's -5. We're given that D of 7 is 3. So if we do some algebra again, the same type of algebra, we get, hold on, sorry. There we go. We also get that D of 0 is 8, which hopefully is true. It's hopefully only one value. So you could do either one of those two processes because it's essentially the same process just with a different value. Now, if say we hadn't been given, D of 7, say that wasn't part of the information that we were given, then we would be forced to use the integral from 0 to 4. So essentially, even if we were given the integral from 0 to 7, if we're not given D of 7, we can't finish it. So make sure when you're trying to figure out which ones to use, you need to make sure that you have an integral with the value that you want and a value that you have. Questions on that? Now, technically, maybe I'll state the interpretation, I just won't write it down. So essentially, this is telling you the amount of the drug left after 0 minutes. So essentially the starting amount. So they started by administering 8 milligrams. Whoops, sorry. Why won't this go away? You can't see it, but there's something on my screen and I can't make it go away. Oh well. All right, so if there are no questions on that, we'll do this next one. So this next one is the integral from 2 to 7 of little dx. So first thing we might want to think about is that using the fundamental theorem of calculus, this would get us d of 7 minus d of 2. Well, those two values, we just have them, so we can just plug them in. So d of 7 is given to us to be 3, and d of 2 is given to us to be 7, so this would be negative 4. Now this, if we were trying to interpret this, remember that we can kind of cookie cutter it. It's the change in the amount of the drug. So essentially between the 2nd and the 7th minute, the amount of the drug has reduced by 4 milligrams. So again, I'm not going to write that down, but that's kind of how you would interpret it if you wanted to. So there's a very similar question, 2 similar questions on your homework to this, where you're just given a bunch of information and asked to find some others. Questions, concerns about that? Okay. Give you like 5 more seconds in case someone's writing something down. Then we'll jump over to 6.6 notes. And again, we're going to get as far as we can. If we want to finish it, I'm not going to lose any sleep over it. All right. Now everything's wonky. There we go. 6.6. So 6.6 is something called U substitution. Now this has to do with essentially finding the antiderivative of something more complicated than what we've been finding already by hand. So of course our calculators can do whatever we need it to, but by hand. So we've been finding antiderivatives of basic elementary functions, but we don't know how to take the derivative of something like the square root of x plus 1 or even e to the negative x squared, which don't necessarily look that complicated, but we don't have a rule to do them. So remember the chain rule, everyone's favorite thing from derivatives. So that's the a reminder about what the chain rule says. So essentially, if anything quote unquote looks like the derivative of the outside evaluated at the inside times the derivative of an inside would have an antiderivative that's essentially a composition, which is essentially what U substitution is. It's kind of like a backwards chain rule. So there's kind of a couple steps that we're going to look at to use this U substitution, which again is kind of like an anti-chain rule, but I'm going to call this U substitution. This one actually has a name as like opposed to the anti-chain rule. So this is formally called U substitution. So essentially what we're going to do is we're going to need to find that inside function. So remember we were talking about inside outside functions way back when. So we're going to need to find the inside function. And we're going to name it U. We're actually going to say let U be something. And essentially we're looking for something such that its derivative is the rest of the problem. That's like the crux of trying to find the U. I'm going to give you some tips for trying to find that U value in a little bit, but that's kind of what you're looking for, is you're looking for something such that its derivative is still in the problem. And that might make more sense when we get to an example in a second. You're going to find the derivative of that U. So whatever you name U, you're going to take its derivative. And we're just going to rewrite it like this. Now, it's almost like we're taking this dx and bringing it over to the other side. That's not quite what's happening. It's much more complicated than that. It's technically a differential equation and fancy stuff. But for the sake of our sanity, you can kind of think about that's what's happening as we're swinging over that dx to the other side. And the reason we're going to do all that is we're going to end up rewriting an integral in terms of U. And again, this is where we're writing down the process before we've seen an example. So some of this might not make a lot of sense yet. And so the point of this is once you replace everything in terms of a U, it should be something that you know how to take the antiderivative of. So we should be able to calculate using our basic antiderivative rules. Antiderivative rules. And since all of the questions I'll be giving you will have to be able to be solved, if you can't do that, something went wrong. So sometimes you might have chosen the wrong u, you might have just made an arithmetic error somewhere. So if you get down to replacing everything and you can't take the antiderivative of it, something's gone wrong. So I'm going to write this out kind of generically first before we get to our first example. So essentially what's going to happen is we're going to have an integral of something that, while it doesn't look like this to us necessarily, technically has this form. And so what we're going to do is we're going to find that inside function, and I'm going to be using colors when we do it in the problem as well. And we're essentially going to say, let u be that g of x. And then we find that derivative. So the derivative of g of x is just g prime of x. And then we rewrite it in this new way, because essentially what happens then is notice that g prime of x dx is at the back of that integral. So essentially what happens is we replace everything in terms of u. So we have the integral of f prime of u. We replace the g of x with what we're naming it. We're naming it u. And then we're replacing that entire back piece with du. So that entire g prime of x dx is equal to du. And then the point is that you should be able to take this antiderivative very easily. And then you just change it back in terms of the original. Well, actually, if I'm being formal, the antiderivative of f prime is just f. So that's a very generic format. So let's get into some specific examples. Now, I will say that this is a complicated topic. And since we're just doing it in one day, it is a little rushed. But feel free to ask me questions. Again, we're getting as far as we can. If we can't finish it, that's fine. So let's do a couple of kind of actual examples here. So say we want to use substitution to solve the following integral. So let me try to leave that generic piece in there a little bit. So we want to find something such that its derivative is in the rest of the problem. So notice I have an e to the x squared, and the derivative of x squared is 2x. So my inside function here, and also remember way back when we were doing chain rule, I said you kind of had three options for your outside function. It was either something to a power, a natural log of something, or an e to the something. There's a similar type of thing here. So since we have an e to the something, the inside function is probably going to be that something. So we're going to let u be x squared. And let me rewrite this a bit larger so that I can start color coding things. So we're going to let u be x squared. So that's going to be this piece here. And we're going to take its derivative. Now, when we do our derivatives here, sorry, I usually like having u over there. Since we usually take the derivative and then rewrite it as some du equals something, what I usually do is I just usually write du equals the derivative dx. So I take the derivative and then just tack a dx on the end. If you would prefer to write it in this fraction notation and then bring it over, go right ahead. But these are done so often that a lot of times you can just kind of skip to du equals the derivative of your u times dx. Now, again, the reason we're doing that is, as stated, this integral was too complicated, but we have a 2x dx. And when I rewrote this integral, I forgot to bring down the dx. So notice that there's a 2x and a dx in the original integral. So essentially what we're going to do now is we're going to replace a lot of things. So the integral Now I'm going to leave a tiny little bit of space. We have e, and the x squared is now going to be u. Okay. And then the 2x dx becomes du. Now don't panic that the 2x was in the front and the du was at the back. Everything was multiplied together, so order doesn't matter. So the 2x could get moved to the back next to the dx, if that makes you happier. But since it's all multiplication, we don't care about order. And we could say, we don't care that that thing's in the front, the other thing's in the back. Order doesn't matter, multiplication. We can just group them together, if you will. So essentially we've said let u be x squared, we found its derivative, and we replaced a bunch of stuff with those u notations now. Are there questions about that? Okay. Feel free to stop me if there are. But again, so the point is that after you do all that replacing, this should be something that you can take the antiderivative of, which this is. We do know the antiderivative of e to the x, if you will. So since that's just u, it's not u squared, it's not 2u. Well, we would be able to take care of 2u. Excuse me. But since that's not a higher power than just 1, we know it's antiderivative. The antiderivative of e to the x is e to the x. So the antiderivative of e to the u, that's still blue, is e to the u. So the antiderivative here is e to the u plus c. Oh, it's lagging. And the last step for these is to essentially always take the u and then replace it with what it once was. So the u was x squared. So we replace u with what it was at the beginning. So u is equal to x squared, so we put the x squared back in. And our antiderivative is e to the x squared plus c, and we're done. Does that make sense? Again, please ask me questions if you have them. This is a kind of hefty topic. No? Okay. Then let's do another one. 2x times x squared plus 1 to the 5th dx. I'm going to need to zoom in a little bit or I'm going to run out of space. So here, we want something such that its derivative shows up elsewhere. So notice the x squared plus 1, if I took the derivative of that, I would get 2x, which is hanging out on the outside. So let's go ahead and say maybe maybe u is going to be 2x plus 1. Now, the nice thing about, maybe not nice, but one of the things about u sub is if you choose the wrong u, your problem's just not going to work out, and then you can go back and try again. It's like you can always kind of test out u's, and if the one doesn't work, then you try something else. So we're going to take the derivative of this, and I'm going to write it as du, and then the derivative, and then dx. So the derivative of x squared plus 1, so 2x plus 0. So let me bring that dx a little closer. So now the point is, again, that 2x dx, coincidentally, also 2x dx like the last one, is going to be able to be replaced by a du. And again, the order doesn't really matter because this is all multiplied together. So I can rewrite this as the integral of u to the 5th du. Oh my goodness, stop it. So again, the du essentially ate the 2x dx. Like Kirby, it just sucked it up and became du. But then the x squared plus 1 just became u. Now notice that the to the 5th power didn't get taken care of at all. That stuck around. And that's just because we took the thing on the inside of the 5th power to be u. And again, the point is once you've done that replacing, you should be able to take the antiderivative of what you're left with. And if you can't, something's gone wrong. Well, we just have a u to the 5th here, essentially like an x to the 5th. So we know how to take the antiderivative of that. It's an anti-power rule. So we can take its antiderivative, add 1 to the need to leave it as u, Add 1 to the power, divide by the new power. Let's see. Your last step is to always take that u and replace it with what it once was. And of course, you could write this as a 1/6 in the front if you prefer. Oops. And we're done. Questions? Y'all always surprise me by how little questions you ask. Okay. Wait like 5 seconds before I go to the next one in case people are still writing some stuff down. All right, so this next one. This one is a tiny bit trickier at first, just because finding the u value always trips people up. Sorry, I dropped a little pen thing. Come back. So again, we want something such that the derivative of it shows up elsewhere. So notice that the x squared plus 4 would also become a 2x. So all of our du's ended up being 2x in this case. But so let's go ahead and try letting u be x squared plus 4. Again, if you try a u and it just doesn't work out, you can always try another one. So we'll have du equals the derivative of x squared plus 4, so 2x dx. So we notice that it's just coincidence that all of these came out to be 2x dx. That the 2x dx is essentially the remainder of the problem. So if we replace, now here is also the other thing that trips a lot of people up. Notice that the x squared plus 4 was in a denominator. So it kind of needs to stay in a denominator, if you will. So it's going to be 1 over u du. Now, just because the 2x was in the numerator, that's perfectly fine. I could bring it out of the numerator and put it in the back with the dx and had 1 over x squared plus 4 times 2x dx. So everything got replaced as it should. Any questions on how that got replaced? Okay. We checked to see whether or not this is something we can take the antiderivative of. It is. This is technically u to the negative first, which is the only thing that doesn't use the anti-power rule. So this would be our natural log of the absolute value of u. And then you just change the u back to what it was in terms of x. Questions, concerns on that one? Okay. Now, some tips for finding your u value. So again, it's kind of like a guess and check in a way, where I just happen to keep choosing the right one. But some tips. If you have, some e to the z, if you will, it's probably the z. It's probably the thing that's in the exponent of the e. If you have something in parentheses, or in a square root, it's probably the thing inside of the parentheses or the square root. It may be a denominator if your function has one. Now that one is a bit less sure because sometimes there's a denominator in the function, but the u value is not the denominator. So that one can be a bit tricky, but it is a common occurrence that if you have one, it's a good thing to at least check if you're not sure. Now, this isn't foolproof either, okay? I'm not saying that this is always how it goes, always and forever. I'm saying that these are usually very good choices for your U. It's very possible to come across some kind of problem in your life where one of these doesn't work and it's something else. But especially in terms of our class, those are very good starting points. Now, this method of U substitution also works if the integrand contains the derivative of the inside function within a constant. So the ones we just did, essentially the derivative of the u value always came out to, well, in our cases, it always came out to 2x dx, but it came out to be exactly what was left in the problem. That doesn't necessarily need to happen if the only thing that's different is a constant. If it's more than just a constant that's different, then either you've done something wrong or it's not something you can use U substitution on. So we'll go through, I think this is, yeah, so we'll just get through as many of these last few examples as we can. We might just be able to get through these two down here, but we'll see what happens. So say I want to use U substitution on these integrals. Let me block myself off so I don't run out of space. So here we have t times e to the t squared plus 1 dt. So using our kind of hints, we're thinking that u might be that that exponent of, and actually let me do the same thing I did kind of before where I rewrite this so a little larger so I can start color coding things. So it looks like we probably want our u value to be this t squared plus 1. So let's take the derivative of that. So we've got du equals 2t dt. Now notice that the thing we have left in the problem is a t dt. So it doesn't have the 2. Since that's just a constant, we're fine. So what we're going to be able to do is we're going to be able to essentially force that 2 over to the other side. Well, I should be careful with my phrasing. We're going to take it over to the other side by dividing by it. So we're essentially going to get 1/2 du equals t dt. And now what I have, t dt, is what I have in the problem I need to replace. Now, if you've seen calculus before, there's one other way you can do that. Well, no, for this one, well, no, I guess you could. Sorry. If you have another way to deal with that constant, if you've seen calculus before and you know one of the different ways to deal with it, go right ahead and do that if you want. But I think that's just the easiest way, and especially since we're running out of time, that's the only way I'm going to do. Because essentially what happens now is when we start trying to replace, we're going to have the integral of e to the u. But now the t dt, instead of getting replaced by just du, it's going to get replaced by 1/2 du. Now don't freak out that 1/2 is in the back. Remember, this is all multiplied together, so order doesn't matter. So we could bring that 1/2 to the front if we want. Essentially, that 1/2 is just going to come along for the ride. Because we can actually take the antiderivative of this. Because the 1/2 comes along for the ride. And the antiderivative of e to the u is e to the u plus c. And then once we've taken the antiderivative, we just replace u with what it used to be. Questions, concerns about that? So even though it wasn't the exact thing we needed, we could still do it because it only differed by a constant. Okay. This is probably, oh no, wait, we go till 2 o'clock. We've got plenty of time. Great. So this next one, let me also rewrite it just so that I can keep doing my little color coding hoopla. So for this one, we've got a square root. So based off of the kind of hints for finding our u, it's most likely going to be the thing underneath the square root. So let's go ahead and try that as our u. See if it works. It's going to work. Let's go ahead and make that our u. So we've got to find our derivative. So we'll write that as du. Derivative of x to the fourth, 4x cubed dx. Now again, in the problem, we have an x cubed dx, so we don't need that 4. But if we divide it over to the other side, so we get 1/4 du equals x cubed dx. Now we can replace. So we have the integral of the square root of u, 1/4 du. So essentially the x cubed dx got sucked up and turned into a 1/4 du. And the thing underneath the square root turned into just u. In terms of taking this antiderivative, I would probably want to rewrite it. I'll bring the 1/4 to the front and then change the square root of u into u to the 1/2. Because if I don't have it as a 1/2 power, maybe I don't know how to take the antiderivative of it. But now that I have it as a 1/2 power, it essentially becomes a anti-power rule. So the 1/4 comes along for the ride. We add 1 to the power, gets us 3/2. Divide by the new power. Remember that dividing by a fraction is the same as multiplying by its reciprocal, which is just that fraction flipped over. So we have 1/4 times 2/3 x to the, u to the 3/2 plus c. You can multiply those two fractions together to get 2/12, which reduces to 1/6. And then I'm kind of running out of space. So I'll just replace at the same time. Replace the u with what it once was. Questions, concerns on that? Am I going too fast? I've never had such a quiet U sub lesson before. Okay. We'll do a couple more then. So I'll leave this up for a couple more seconds in case people are still writing stuff down. And we'll just do as many examples as we can in the next 10 minutes. All right. Note that U substitution does not work if the derivative is missing anything besides a constant. So an example of that would be something like x to the 5th times the square root of x to the 4th plus 1. So kind of similar to the one we were just looking at. So we would probably guess that we would want the u value to be the thing underneath of the square root. But then when we take its derivative, we get 4x cubed. Now technically, in this integral, if I break this up into x squared times x cubed, I do technically have an x cubed that shows up there. Now I don't need the 4 just like last time, so let me kick it over to the other side. But essentially, if we were to try to do this, so we have our u, so we can replace the u with the thing underneath of the square root. And then we could take this x cubed dx and replace the x cubed dx. But if I start replacing things here, I get the integral of x squared square root of u 1/4 du. Let me just color code. Now, because there's that extra x squared at the front, I can't take the antiderivative of this because I can't take the antiderivative of something that has two variables in it. So I'm stuck. And so, what's the word I want? U substitution. In terms of as much of a U substitution as we do, would not work here. There are some problems where you can do some fancy algebra and get it to work. This might be one of them. No, I don't. Well, maybe. Anyway, in terms of what we do, we wouldn't worry about it. But in terms of U substitution in general, there's sometimes some fancy algebra we could pull out. But if there's ever anything where you get a U and can't replace everything up to a constant, then U substitution just doesn't work. Anyway, so let's do a few more examples. So, say we want to find the integral of t squared over 1 plus t cubed dt. So this has a denominator. So while it may not be our U, a good choice to start off with would be let that denominator be our choice of U. Doesn't always work, but again, with these things, you can kind of try it. And if it doesn't work out, then you can try something else. So we take our derivative. We get 3t squared dt. So if we start thinking about what's going to be replaced here, we're going to replace the denominator with u. And then we have a t squared dt. Well, that did come up in our derivative, so it looks like we picked the right u. And the only thing that's, in our way is this 3. So we can just bring that over to the other side as a 1/3. And then just be left with the t squared dt that we'll use to replace. So if I start replacing things, again, since the u, the thing that we're setting equal to u, started in a denominator, it needs to stay in a denominator. So we need to have 1 over u. And then the t squared dt is going to get essentially, sucked up and transformed into a 1/3 du. And now hopefully this is something we can take the antiderivative of, which it is. This is another one of our natural log ones, because again, 1 over u, the 1/3 is going to come along for the ride. We'll get the natural log of the absolute value of u plus c. And then our last step is to just replace that u with what it originally was, which was 1 plus t cubed. Questions, concerns? All right, technically there's 3 more. I think I'm just going to end on this next one. We'll do this next one, and I don't think I'll have time for the last 2. The last 2 are very similar to ones we've already done. Excuse me. So I'll maybe write down the u values, and I'll write out the full thing for the thing that I post on Blackboard. But we'll do this one, and then we'll call it a day. So for this one, we have 2x times 3x squared plus 7 to the 5th power. So here, since we have something inside of parentheses, it's probably going to be the thing inside of the parentheses. That's going to be our u. So let's let u be, oh my goodness, be 3x squared plus 7. We take our derivative, so du equals 6x dx. Now this one is actually one that gets a bit more, there's a bunch of different ways you could do this one. I'm gonna do that way because it's the most like what we've already done. So notice that, so we're going to replace the thing inside with u, and notice that we have a dx, and we technically have a 2x. Now I know that there's a 2 contained in the 6, and again, there's a bunch of different ways you could do this. You could rewrite that as 2 times 3x, and then just take the 2x and swing the 3 over to the other side. But what I'm going to do, just because it's as close to what I've been doing already, is I'm just going to take that 6 and move the 6 over to the other side. So I'm just going to have x dx. Because then what's going to happen, and it's perfectly fine, is that in the original integral, that 2 didn't get replaced by anything. That's fine. It's a constant. It's okay if it doesn't get replaced. So again, while there's a bunch of other different ways you could do this, and if you know them, feel free to do them. But I swung the whole entire 1/6 over to the other side, so the 2 is going to stay. The thing inside the parentheses becomes a u, so we'll have u to the 5th. And then the x dx gets essentially sucked up and turned into a 1/6 du. So that 2 didn't really have anything to replace it, but that's fine. Now we can simplify those constants a little bit. We can do 2 times 1/6 to get us 1/3. So we'll have 1/3 u to the 5th du. That is something we can take the antiderivative of. The 1/3 is going to come along for the ride. Anti-power rule, add 1 to the power, divide by the new power. U to the 6th divided by 6 plus c. So we essentially get 1/9. No, that's not it. 6 times 3 is 18. 1/18 u to the 6th plus c. And then replace u with what it was originally. So that one had a slightly different trick to it because it had like an extra constant, if you will. But even in situations like that where we can't replace everything, it's okay as long as it's just a constant that we're not able to replace. Let me tell you your u values for these last two. And then again, we'll call it a day. And again, I'll write out the full answers before I post these on Blackboard. For the third one, your u is going to be the x cubed from the e. So if you have an e to the something, it should be that something. And then in the fourth one, it will end up being your denominator of x squared plus 1. So I'll do those full out before I post them on Blackboard. Otherwise, let me scroll back up to this one real quick. Oh, I did. I wrote 1/8 instead of 1/18. Sorry. 1/18, 3x squared plus 7 to the 6th. Thank you. If you have questions, feel free to stick around. Again, I'm very surprised there haven't been any, so don't feel afraid to ask me questions on this. But otherwise, I hope you all have a safe and happy Thanksgiving, and I will see you next Monday for our final exam review.